All right, welcome everyone to today's webinar, which is going to be on how to analyze electrical impedance properties of piezoelectric sensors. And I recognize that I think I haven't really covered sensors very well in my webinar so far. Most of the stuff has been on actuators. So we're going to do a lot of basics on sensors, piezo sensors, the basic way to understand it, not getting too analytical, but enough that you can you can work through other problems, or at least analyze something you've purchased. That's also much of the case of many of my clients and perhaps many of you. So we're going to discuss what is piezo sensor impedance. And it's not what you think it is, especially if you come from using actuators or measuring this actuation responses. Many of you may have seen this kind of resonance anti-resonance. So how does it relate to the impedance response? How does it interact with electrical measurement circuits? I'm really going to describe a bit of, there's going to be a bit of blackboarding in terms of like how do you just understand really basic equations and frequency response. I'm going to be talking about charge amplifier versus voltage buffers or voltage amplifiers. Um, Oh, and hopefully, I hope that this will be a great introduction and give you guys a good understanding of electrical impedance and piezo sensors and how do you start that understanding. Because a lot of times piezo sensors are treated as a black box, piezoelectric devices. And the reason it's treated as a black box is because nobody has perhaps clearly explained in a consumable format, which is very accessible, how do you analyze its devices? So I'm here to provide the world, starting with you all, that information. Um, so let's talk about piezo sensors. A few intro slides, and we'll get into some, introducing my company and also my sponsor for these webinars. So piezo sensors, you're watching this video or you're listening here live, you know what they are. So there are different types, though. I'd like to bring to your attention. They're single frequency, and maybe some of these devices may span different categories, but for in general senses, there's backup sensors like the all right, this is kind of a big ant in front of me. Anyways, back to the webinar. So the backup sensors, like the 40 kilohertz things that you might see on your car. There's level sensors, which are used to measure the height of fluid. So they can either be mounted on the fluid side or on the air side. If they're on the fluid side, they're usually typically in the megahertz frequency range, and also medical ultrasound, which uses mostly, I believe, single frequency actuation. Um, but they also then actuate, but they also then receive. So there's that double function. So single frequency, double function. That's usually how we roll in that area. But there's also the actuation. So there's also for broadband, so measuring a wide frequency range, like the typical idea of a sensor. Contact microphones for musical instruments, and accelerometers. If you consider an electric microphone has piezoelectric properties. That's also included here. So broadband, wide frequency range. It's less typical, I would say, for some of my clients, but yeah, these are what exists. And energy harvesting, it's kind of an odd case of a sensor. Let me get rid of this thing. It is kind of a sensor in the sense that you're applying a force and you're relying on the electrical characteristics. I don't believe there's any practical application in terms of something that a real company has produced that is selling. So there's a lot of research in this area, ideas like, oh, we could use it for this, but there has been use in active damping. Yes, active damping has been used with piezoelectric elements. And also piezo igniters. You may know, like from your barbecue grill or something, you press the button, there's a plunger that spring and hits the piezo element and creates a spark. That's kind of like it's not a sensor in the sense that you're not measuring anything, but it is a force to electrical device. So it's kind of interesting there. There's also the DC type, low frequency, and I'm just going to designate that as like a force sensor or a strain gauge. They're less common for piezo elements to be used in this way, and we'll discuss why. But it can be used as lower frequency sensors. We may even consider our preloading, the bolt clamped ultrasonic transducer, the power transducer. During that process, we torque down the piezo stack, and we use the stack itself as a force sensor. There's an interesting example, but there's also other ones that are dedicated for just sensing itself. All right. And here are some examples. We have, I mentioned the broadband transducer. Here there's the guitar and there's the saddle, I think it's a bridge. And underneath that, there's this like long piezo element here. I'll zoom in maybe a little bit. And there's multiple elements in this, and it's mounted underneath these strings, which then pick up the frequencies which are generated by the strings. There's also this, everybody's seen this one, this Arduino pulse echo range finding transducer. We also know that you can use a single transducer for this, but in this case, the electronics become a lot more simple if you just use two rather than one. And here's an accelerometer where you have a piezo element sandwiched in between multiple mechanical pieces, and then it resonates, and not resonates. Then you design these different mechanical components to get the right frequency response, because the piezo element itself would not exhibit enough strain if you did not attach other proof masses and things on top of it. And you can also just plain find elements and just slap it on a piece of substrate and start measuring stuff. Like you attach a bender element, or this patch, like softer patch elements, which can generate enough voltage based on almost any stimuli to be able to create a frequency response, or something that you can just measure. So benders are very common with sensors because they exhibit much more displacement than solid elements. That's something you'll see in most cases, because the design of actuators is very different than sensors. Now for the advertisements. So my webinar sponsor is Piezo, PI ceramic technology. They provide many different types of piezoelectric formulations, similar to other manufacturers. However, I highly recommend them because of their consistency and reliability, and the fact that they're kind of experts, not just producing the ceramics, but they are developing new ones. And all the clients and all my interactions with this company have been very high quality in terms of the depth of their understanding, their ability to support clients, and produce consistent properties for their piezo ceramics. So for that reason, I recommend them for you all, and for anybody searching for a piezo ceramic vendor, because there's many choices. There's Asia, there's if you're America, there's also Europe. This is one of the European companies, but this one specifically I've had a great experience with, so I recommend them. And they have US reps in all over the world, including the United States. So I recommend them, and that'll also support the webinar. If you do contact them, let them know I sent you. And also click the links on the website or wherever I put links, because that just helps track that information. So I provide consulting services for companies developing ultrasonic transducers. It can be confusing at first. Sometimes it's simple to get started, but it's confusing to get a good product working. And that's me right there holding a marker. So you can hire me for help in all different types of areas, from assembly guidance to planning, electrical, mechanical analysis. There's a whole bunch of areas that I'm very adept in, and I can fill a lot of the gaps. Many times I work with companies who have staff, but they're kind of maybe augmenting my expertise to them so they can really proceed efficiently, because there's a lot of holes and things that can be missed, and lacking, and skills that are lacking. For example, finite element analysis and piezoelectric materials. You don't want to necessarily start that by yourself for the first time. You may get wrong results, and you may not understand what exactly the results mean. and how they translate to experiments. So I've worked on many different devices. Many of the devices I work on are both clamped Langevin transducers, but my expertise kind of is broad, and I've also worked on sensors. And yeah, contact me if you are stuck in development, or you could just use a boost. And with that, let's talk basics and go further. And I think I'm planning to continue my discussion of piezo sensors. So maybe if what you wanted is not covered in this presentation, you may find it in the upcoming webinars, or definitely request it here, because this is a broad topic, and because it's not one that I have covered previously in my webinars, I felt it important to start from the beginning, but quickly head kind of toward a practical level where you have an understanding that's useful. So yes, I'm very much a fan of useful understanding, very not much of a fan of extraneous information, especially for people who are trying to develop the devices rather than kind of go all calculus and all that kind of stuff on the information. So piezo sensors, we know what those are. There are basically you apply a force and you get a voltage, and that's a very simplistic understanding. Applying a force, getting a voltage. And we know the converse effect, which is maybe more famous, I'm not sure, but you apply a voltage and then you get a displacement, or you get a strain, or you get a force. What actually happens in the converse effect, if you look, if you want to talk about a globally true understanding. So this is important, actually. This is very important to understand what the chain of operations is in the development, and the how the phenomenon is exhibited in the real world. For the actuator, we apply a voltage, but we're really applying electric field, and that's practically the same. I'm not going to argue with that here too much. And then we commonly think that there's a displacement or a stress. So a better way to think about the converse effect, I won't go too much into this, is that the voltage creates the stress, and the stress creates a displacement, which relaxes that stress and creates a zero stress state, if it's allowed to. With an ultrasonic power transducer, because of the inertia of the attached components and the piezo elements themselves, that inertia, that stress generated is not allowed to completely relax. So it actually ends up developing an alternating force, not just an alternating size difference. And this is also true with lower frequency actuators too, but it's really highlighted with the resonant devices. And in a similar way, I said, okay, you apply a force and you get a charge, or you get a voltage. That's not really what happens. You don't just apply a force, because if you apply a force, you don't necessarily get displacement depending on your boundary conditions. So let's talk about that. So actually, the best way to think about this is you could say applying a force, because you can't get displacement without a force. So let's start this. You get a force or stress, okay? And then that takes you to a displacement or a strain. This is really key, because if you stop the process at any one of these points, you're really not going to provide a displacement. And how do you get and so if you apply force, but you also have alternating forces on the other side that to counteract that, then you don't really have a result. So you need that force to cause a displacement, basically a shape change, a strain. Because if you take a piezo element and you move it back and forth, hey, look, it's displacing, but there's no strain internally. So the strain is what's causing the voltage, but it's actually charge. So what is very uncommon for us is to think in terms of charge. What is very common for us is to think in terms of voltage, because that's what we measure with an oscilloscope. Everything we do, we measure voltage. And maybe if we're even a little bit more advanced, we can measure current, but never do we really look at charge, which is actually the fundamental thing that happens with the piezo element. It is a charge generator. It is not a voltage generator. If we were in a classroom setting and I felt comfortable enough, I would ask everybody to repeat after me. Piezoelectric elements, sensors create charge, not voltage. But anyways, we're not going to do that. So let's continue to the next slide here. Okay, so this is what I was just saying. So we have a force, we have a displacement, which is going to cause a strain, and that causes a charge, and that causes a voltage through the capacitance of the piezo element. And if at any point we stop this process, then we're affecting the next step. So you can't get force and displacement and strain. That's understood. That they're fairly balanced, but there are unique cases where you can actually generate displacement without force, I guess, and the way the way you do that is when you apply a voltage or you do something thermal. That's how you can get a strain without a force. But that's really not what we're talking about. We were talking about more of the mechanical sensor part, not of the other types. So that creates a charge and it creates a voltage through the capacitance. So so if you insert anything in between here, uh, anything over here, like any other circuit components or things, you're going to change the amount of voltage you develop. And this is where the whole idea of capacitance, or sorry, the whole idea of the impedance of your sensor becomes important, because piezoelectric elements are charge generators, and your transducer has a specific relationship between the input force and the generation of charge, assuming you're working under the resonant frequency. I don't really focus on resonant sensing. I think I can. I think I should in the next seminar, because we have a huge amount of devices that work on resonance structures, like the pulse echo. You emit 40 kilohertz and receive it back. At what amplitude are you receiving it back? That gets to be important. But today we're mostly doing, or we're talking general and also lower frequency. It's more simple to analyze and explain, and then honestly that's what I had time to prepare. So let's just take the basic piezo sensor. It's important to know this if you haven't ever done a calculation like this, to know what amplitudes and things are there. So if you have a force of 100 newtons, and this is also assuming that this piezo sensor is untethered. What does it mean to be untethered? So like let me just make a new slide. Okay, so if you have a piezo element and you bond the bottom of it to something and you put a force on it, it'll expand to look like this. That is not like a pure good theory thing. That's not pure strain. Uh, that's not force. This strain is going to be less than less than a case where you don't have it tethered, or let's say you just have these. This never happens. You never have pure roller bearings, right? Roller. But if you push down on this equally, this will just flatten out equally. So my equations, the equations I'm going to be showing, that, charge equals, this is for a piezo element. This is actually absolutely true. You can prove this out in FEA too, that the charge generated equals the force times the charge coefficient, assuming that you're pressing on the top evenly. But it's not true for this case where you bonded it on the bottom, because now they're opposing forces. There's different stresses here. This is uniform stress all throughout. So the strain and the stress aren't related. So it's not, you can't just use the 333 coefficient. This is like, many times it's the best case for a single element, but it's really not going to be what's witnessed. But I'm doing simplifications here. So note that however you bond and you have your transducer, if as long as it's not sitting with perfect stress applied and unroller supports, which don't exist in reality, you won't have these equations. But let's say we do, because the basic ideas still work in terms of calculations. So we have a force applied, 100 newtons. We have a charge coefficient. Usually the charge coefficients are between 300 to like 600 picocoulombs per newton. I'm just going to assume 100 picocoulombs per newton, just for simplicity's sake. This simple equation can be proven to be true for this basic element here, this case here, where you just have a perfectly applied stress on an element, and it's not constrained in any way. In that case, we have 10 nanocoulombs of generated charge, and then through the capacitance, I'm just going to assume this capacitance here of 1 nanofarad, we get 10 volts because Q equals CV. The Q over C equals the voltage, so we get 10 volts. So this is, I mean, 100 newtons is a lot, but that's for the sake of calculations. And you may wonder about, this capacitance, and if we reduced it, like if you had a 300 picofarad or 200 picofarad sensor, your voltage would be 5 times higher. It'd be 50 volts. And that's interesting, but it's also not as important as you may wonder, because for sensors we can amplify voltage, but we need enough signal and transducer impedance and charge generation to make it all sing and work. So let's consider AC. So before we were doing DC, like low frequency, or let's say static, we applied it and then we did the measurement, like before and after. So what if you consider AC, where you have a frequency? So the force applied is equal to a constant force amplitude, and we have our our amplitude functions, like the charge amplitude is still going to be equal to the force amplitude times the G33. I am not showing a resonant case, which is going to be different. There's going to be higher charge developed at resonance. But the way to represent this in a circuit diagram would be, let's assume this is the capacitance here. I think I can do highlighting. If anyone has any questions, please go ahead. So this is the capacitance of your piezo, and this is, we're not usually in the circuit program. I mean, like in circuit simulations, you don't have access to like charge generators. That's typically not common. So if you do have, so the current here, this is a refresh. The integration, or the derivative of charge, basically the charge rate, is current. So essentially, you're actually developing current. So the current nominally is the charge integrate with the derivative, the rate of change. So that's just it is the frequency. So the charge rate. So if you do a circuit simulation, you want to divide this amplitude, whatever you set it at, by frequency. If you're assuming it's like a constant force excitation, you may have a situation where you have a constant displacement excitation, in which case you don't need this, so you have a constant velocity or excitation, which you wouldn't need this component. But typically, if you're going to be doing a circuit simulation with constant force, you're going to need to divide by frequency in order to say that there's a constant force, or which means a constant charge being put into the system. But because the frequency is changing, as you go to higher frequency, you're actually generating the same charge, but because the same charge has to be changed faster, we don't. Yeah, we need to divide basically by frequency. So here I drew, and just for like understanding, like when we're going to be measuring our piezo sensor, we're going to be connecting with some wires, and a lot of the cables and all that, that is a huge deal, because if you have low quality cables or long cables, they will cause more capacitance. On all the connections, they have capacitance and resistance to it. And the ADC itself, whatever you're measuring with it, oscilloscope, we say it has 1 mega ohm or 10 mega ohms, whatever kind of probe you're using. So all of those things are going to affect the voltage measured, because the charge generation rate, or the charge that's input, is going to be the same, the charge, because but the charge generation rate is going to be increasing. I think I'm getting a little something confused here in my brain, but hopefully you'll still hang on. So the charge generation rate is going to increase with frequency as you go to a higher frequency. I'll correct for that sometime. Maybe I'll correct for this on the slides. Um, um, so the charge equals the force times the d33 coefficient. So the current is going to equal the frequency times the force times the charge coefficient again. But however, like if you try to draw like an impedance analysis diagram, it's not going to be correct because you're not inputting a voltage to the system. You're really inputting a force. So to say that something has an impedance as an input output, that is going to be a little bit dubious because if you want to represent the circuit and the charge generation in one component, you're not going to be able to do that in a simple way as you would when you literally apply voltage and you literally get a current back. That's the same domain. When you're hopping domains here, you no longer have a similar case. So you'd have to make assumptions. You'd have to kind of put equivalencies. So still, we're trying to look for. We have a charge generation rate, and we have an attached circuit. What we're really actually interested is how this attached circuit affects our voltage. So, because if we have a higher force, so if we have a different transducer, well, basically higher force, and that that will change the voltage too. But in order to get a more cohesive or like a consistent definition, we're going to stay in the electrical domain in terms of defining impedance, which means we're kind of leaving the charge generation rate out of it. And so we'll discuss more about that here. So the sensor impedance doesn't really account for the voltage generation rate. But only the voltage reduction. So how the voltage which is generated in the open circuit condition, assuming like a perfectly measured measurement circuit, which we're going to be comparing when we attach these components, which is, let's say, representing the ADC and the cabling, how the voltage is reduced. That's what we're talking about when we're talking about the comparison between these two systems. All right. So actually, kind of for low frequency, the impedance of the sensor is just the impedance of the capacitance of the transducer. That's the simple way for low frequency for analysis. So the charge generation rate or the current is actually dependent on a lot of things. So we were just talking about impedance, but let's just get back to the charge generation rate for a second. So that's going to depend on the force, the piezo coefficients, and also the geometry. So whether you have a more simple analysis for a D33, like let's say a cylinder or a disc or something, or you have a D31 where you actually have the aspect ratio of the length and the thickness, which can amplify the voltage depending on the direction of the applied force, or you have a bender element, which is also another way which large voltages and strains are developed for low forces. So low force here creates a large strain based on the transducer topology that you're having, because bending, you have a amplification of strain due to kind of lower stiffness. So for a bender, so the voltage is actually dependent on the charge over the capacitance. The charge is dependent on the strain developed in the element, and the capacitance is proportional to the thickness, inversely proportional to the thickness of the piezo element and proportional to the area. So for a bender element, like a unimorph or bimorph or one of those, really common discs with a piezo element attached to it, you type in piezo bender, you'll come up with one, or guitar pickup that you can easily purchase. 1 second here. So it has it has a large capacitance because it's very thin, but it also will generate a lot of charge because it bends, so that creates a lot of strain in the element. So the voltage is high as a result in general, still, even though the capacitance is higher. But so you'll easily be able to generate a voltage with your like finger or by tapping it or things like that, that you can easily measure. And because the capacitance is high, it's much more stable according to any circuit that you attach to it. We'll talk about that in a second. But the frequency response is quite low because of the stiffness is low. For a D33 element, the capacitance is low, which brings up voltage. The charge is low, because you're not getting any aspect ratio or geometrical amplification of charge. So generally the voltage is lower and the frequency response is higher. For a D31 element, but you can also make this really long, this D33 element, which is what's used in the piezo igniter. So for the piezo igniter, you have a long cylinder, and due to the length, the thickness is really high, so the voltage is extremely high, so that's why you have sparks. So that's not to say you can't generate a large voltage with a D33 element if you design it in a specific way, but it may be impractical because you want that thickness is important for your application. Usually sensors we want to have as kind of least invasive as possible and not to be the entire system. So yeah, I see something in the chat, so I'll get to that in a minute. So this has a lower voltage and it has a higher resonant frequency, which is quite important for some cases actually. So for a D31 element, it's not quite a bender, but it's not a D33 element. So sometimes it can have a relatively, you could say low. Actually, it is a high capacitance sometimes. So I guess it would be about the same as a D33 element in general, like very generally speaking. However, the charge generated is much higher because we're utilizing the aspect ratio. So generally, the D31 element in that case is going to generate more voltage, a bit more charge, and it'll have since this aspect ratio you're trying to make it a bit larger in some aspects, it will have a lower frequency response in general. Okay. So back to the sensor. So let's assume the voltage of the sensor alone would have been 1 volt, and because we generated that 10 nanocoulombs. If we had, let's say, an attached capacitor of 3 nanofarads, we would end up with 0.25 volts because, 1/4, 4 nanofarads total. So the total capacitance is 4 nanofarads. So, and the charge is going into both are the same. So 1/4 of the charge is stored on one, and 3/4 are stored on the other. So, and because of that reason, we have 1/4 of the voltage. And because this attached impedance source or this attached capacitance is the same type of impedance as, the same frequency response or characteristic with frequency as this other, as our piezo capacitance, assuming we're below resonance, we will have the same response across throughout. So if we have the same voltage, and I'll just let's make a new slide here. And I want the slide without any thing written on it. So if we have a frequency response, so for constant force, I think I'm going to show this later too, so I'm probably being redundant, but we'll have a constant voltage for the frequency, and if you put like, this is the frequency of the crystal alone, I'm just going to write X, not that makes any sense, but, and then the crystal plus that other capacitor, plus other capacitor, this would be 1 volt, this would be 0.25 volts. So the frequency response would be the same, assuming that the same voltage, because voltage is dependent on Q equals CV always for this case. Q equals CV. So because the charge is the same and the capacitance is the same throughout frequency, the voltage generated is the same, even if the current is increasing. So I misspoke earlier. The current is actually increasing with frequency. So you probably have to multiply this by you probably whatever current you set, you'd have to multiply it by frequency in order to keep the same voltage for the capacitor. That was a mistake earlier I mentioned, but and I'll be getting into the circuit simulation of it probably in the next webinar. Next webinar. So what happens if you have a resistor here? And I just blacked all this out because this is not true anymore. It's not true across frequency. You're not going to have that constant voltage response for a constant force anymore. So now, assuming there's 1 mega ohm, what would be the actual voltage measured on the ADC? It's assuming it's a purely resistive load. And this is actually what would happen. And if you can see in very light gray, I put Q dot here, and there's this marker here. So the charge generation rate across frequency, or the current, actually the charge generated is the same, not the charge generation rate increases. You know, I always correct myself when I'm trying to teach something. But anyways, so the charge generated is the same, but the current is going to be it's going to interact differently. So I would actually say I'm gonna take this back. I no, I have the right to be wrong, the right to correct myself. Two rights we should always take advantage of before it's too late. Okay. So, and I don't want to make this too long, but so for the crystal alone, so the amplitude of charge is always going to be the same, and the amplitude of current generated is going to increase with frequency because, well, you can think about it multiple ways, but you know, this is the same. I'm just going to draw this too, and this is just force. Force is constant over frequency, so the current is going to be constant so over the frequency. But when we attach a circuit component, we know the charge on that capacitor is not the same anymore. However, the charge generation is the same. So we can still take this part and say this is gold, but this is not no longer going to be the charge on that capacitor, because that would mean it's the voltage necessarily. So what do we say here? Because so the charge generation rate is still the same, Q, but now we can't say that this Q is exactly the same because this going into both. So that same charge or current is going now into two components instead of one. Therefore, and I'm going to erase this. Refer to previous slide correction. Therefore, what's going to happen to the voltage is at low frequency, the charge will not be allowed to develop because basically all the charge will drain. But as the frequency increases beyond a certain point, and you know, as you can kind of see, these two form a filter, that the voltage will stabilize because the generation of charge. So because this component will now be absorbing much more of the charge in comparison to this one, because it has to do with the ratio. The ratio of impedance changes. So I can draw that out too, because I guess that's the point of this presentation here. So the ratio of charge, I want a regular slide without. If you take this, so this is the impedance. So the impedance of our capacitor decreases with frequency, and the impedance of the resistor stays the same. ZR and Z. So because the capacitor has much lower impedance, it kind of dominates the result, and hence it also dominates the current. And then at high frequency, we again get this trend where or the charge generation rate, again, becomes the current on that capacitor. So let's do the calculation. Basically, so charge equals capacitance times voltage for our capacitor, and voltage equals current times the resistance. And this is not just current, this is current over that resistor. And this is current in this capacitor whenever we define it. So if we define the impedances of each of these components, and we do really kind of basic analysis here, we'll end up with, 1 over the total impedance is this result. And this is just basically going to tell us that at low frequency, the resistance basically causes the voltage to be 0. And at higher frequencies, at very high frequency, there's the capacitance dominates and it takes all the current. And hence the voltage, the current is actually stored and stored on there, and we develop voltage. So essentially, I just had some algebra here, but at low frequency, you basically have no voltage, and at high frequency, you have the voltage according to what you would expect in a perfect scenario. This is really important for people trying to measure low frequency changes with an oscilloscope, which even has 1 mega ohm of impedance. It's like, oh, 1 mega ohm is really high. Well, that 1 mega ohm, along with the capacitance of your transducer, is going to form a filter. So it's going to have a roll off, and it's also going to not allow you to measure very slow changes. I think 1 mega ohm is enough to measure those slow changes, but you'll see the voltage kind of very quickly drop off. And if you've seen my previous videos, and when I try to measure the voltage on a piezo element that I squeezed and I try to measure the charge, it'll go down very fast if you measure it even with a 10 mega ohm. So you cannot use this circuit actually at all to measure DC. Like you can't use your oscilloscope to measure press a piezo crystal and measure the voltage. It's just going to deplete immediately, with the time constant of these two components. So it becomes very important to understand and to appropriately buffer or protect the voltage or charge that your piezo element is producing, because anything you attach to it is going to create a filter. And it's going to either create a filter and also reduce the voltage amplitude. I want to bring to your attention something interesting, because I started becoming curious about this, and because we have the electret microphones, those little small microphones that are relatively simple to purchase. They look, they kind of look like this. And they basically have a dielectric element which has been polarized, so it has piezoelectricity. And when the sound comes to it, it changes in shape a little bit, and that change in shape also generates a charge or a voltage on this little capacitive element there. So this is not PZT, it's like a polymer, and there's some trapped charges which cause the piezoelectricity of it. And those are the typical things when you plug in you plug in a microphone to your computer. That is the type of microphone it's using. And we kind of wonder, like, hey, like, how does that work? Like, is our like a laptop like really high? Does it have a really high like impedance to it? Like, what's going on there? And also, very specifically, one of the reasons this is very important is because of noise, especially with audio. When you're doing ultrasonics, there may not be as much noise to worry about per se. But especially when you're doing audio, because of the 60 hertz noise, and it becomes concerning as to the length of the wires and how you are like measuring and allowing your computer to measure that. So if you open one of these microphones, you'll find on the back side of the microphone there'll be something that looks like this, like a little circuit component. It has 3 terminals, just like this one here. and it's actually providing amplification, and it's kind of clever how this works. Maybe I might talk on this too long because I find it very interesting, how simple this amplification system works. But um, there's this electric microphone. We talked about capacitance. This has a very low capacitance as well, so you don't want to have a long cable which would zap. Like if you have, let's say, 10 picofarad capacitance and you had 100, 200, 300 picofarad wire, along with a bunch of other connections, that's going to really eliminate your signal. And when you start to amplify that back again, you're going to amplify all the noise that comes along with it. So what it does is that it provides a bias voltage to a transistor, a JFET transistor, which is what this is, and the electric microphone is not interfaced directly to the laptop or to the computer. Rather, this forms basically a small amplifier, which I think I may have discussed at one point, but I can discuss how this works because it's kind of interesting in comparison to what we just throw in an op amp. Getting discrete is very interesting sometimes. So it performs a voltage. It provides a voltage buffer. So this has a variable resistance according to the voltage applied at its gate. And similar to a MOSFET, it has a small capacitance associated with the gate, but it's constant, and you can put this very close because the JFET is not mounted. It's not inside your laptop. It's at the back side of the microphone as close as you can get to eliminate noise and reduce as much as stray circuit component that might exist as much as possible. So essentially, what this does is that although this, let's say I'm just going to give it a number. I couldn't find what the capacitance of. Let's say it's 100 picofarads. And I'm just going to give it a value. Let's say it's like 10 mega ohms, whatever, at the frequency we're trying to measure. I'm just going to write a number. But the output here, it ends up being, I'm just going to write a number again, 3 kilo ohms based on this resistor and this JFET. So basically and also provides amplification based on this circuit. But this circuit and this system is much less susceptible to noise. And hence we can both amplify the voltage and provide a buffer such that weaker sources of noise, which may then compete with the signal of our transducer that it's generating, or the charge. It's going to compete with the charge that's being generated of our transducer. It no longer has to compete because you put an amplifier here. So it both allows you to attach other components. Like now you can attach your filter, whatever filter you like to attach, or whatever you like to do here, you can do it now without worrying about what it's going to do your transducer. So you effectively separated. You made your sensor a black box basically at this point, in the sense that you no longer have to worry about your transducer of voltage or transducer capacitance as much, although it's still important because in this case it'll still have some impact. So this is the kind of a op amp voltage follower. So whatever voltage is generated here, it's going to be generated on the outside. However, it is much less susceptible. It can be also made into an amplification format, but it also is much less susceptible to noise because it has a lower impedance. The other case, and I described the voltage buffer here, so it can decrease the signal impedance. It makes it less susceptible to noise, so attached circuits will have less impact on the signal, or you can actually make it intentional by putting filters that you want, not that you have to live with. And you should place it close to the sensor in order for much less noise to be put on the circuit. And as far as the charge amplifier is another completely different type of case where it's an integration circuit effectively. So the sensor charge is depleted by the amplifier. So at any point, the voltage on the sensor equals 0 because all the charge is then flowing into the op amp, which then gets stored into the external kind of capacitor in the feedback loop. So the measurement is not affected by cable capacitance because it's only measuring charge. It's only integrating the current flow, and there's no current caused by the capacitance. So this is the inherent frequency response is due to there's an inherent frequency response, and it's due to the integration of charge. So you will have a different response because of the integration rather than the proportionality which the voltage amplifier gives you. And I'll just kind of go to the last slides quickly. This is the impedance response that we measure from voltage and current in a piezo device. It's not the same as what we would have from a sensor. We don't have this kind of resonance, anti-resonance phenomenon exactly. There is a resonance occurring because there's a mechanical structure. If it's allowed to occur, I'll say, based on the mechanical boundary conditions. But if it's based on forcing, if you apply a force to this specific element in a perfect way, what's going to happen is at the anti-resonance, there'll be a more charge generation. So if you draw this diagram, and I'm going to write Q, it'll be stable. And then when we get to the anti-resonant frequency, it'll peak and it'll go down. And as you keep going past the resonant frequency, now suddenly your piezo element behaves stiffer, more stiffly. If you provide a charge amplifier circuit, you'll have a peak in your signal at the resonant frequency. So this would be the short circuit, and this would be the open circuit case for for the analysis. So for sub-resonant for sub-resonance, you can consider the capacitance and the charge to stay the same. And the open circuit is actually kind of like the sensor response, where you're disturbing your signal as little as possible. Let's say you have the perfect amplifier, you have no kind of additional components attached. So in that case, it's the open circuit resonance, which is the anti-resonant frequency. And if you had a charge amplifier, or you honestly, if you shorted it on purpose, if you put a 1 ohm resistor across your device, and somehow you're able to amplify that appropriately, then you would actually resonate. Your sensor would resonate at your resonance frequency that you would measure from this response. So this response is not exactly appropriate because you're using your force, you're putting in a force, and you're getting out a voltage. So there's a conversion needed. But in general, if you were looking at, you would actually be needing to modify your current generation source. Because the generation of charge, or of current, would be different, and I can kind of, it wouldn't be this model. It would be more similar to a transformer, and that's something, a transformer model with voltage and current kind of being represented a bit more. You take it one level of abstraction higher in order to get more fidelity in how you use it. But in most cases, we can just work with our, for a DC device, or you can work with your capacitance and your charge generation from from a current source. So in summary, we talked about charge generation from strain, capacitance, which comes from geometry, and the frequency response, which also comes from the geometry of your transducer or your sensor. The attached circuit components will reduce the voltage and form filters, and also there's a huge susceptibility of noise from the environment. So the voltage amplifier converts voltage to voltage, basically. It decreases impedance, so it's less susceptible to noise. And the charge amplifier then creates that voltage, not really voltage, but it takes the output charge and integrates it. So it also effectively removes the effect of noise, and also removes the effect of the impedance of your sensor. There's no high impedance state, so we looked at this anti-resonance case. Like anti-resonance or sense, it doesn't look similar. Basically, the sensor only has one resonant frequency. It doesn't have two. Like it doesn't have a resonance and an anti-resonance, because it's just mechanical to electrical. So the sensor's mechanical resonance, the highest generation of charge occurs. And after that point, you'll have less response simply because your sensor can no longer exhibit strain anymore. So with that, I'll open up for questions. I'm glad I didn't plan more for this. Let me see here. All right,